historical approach to particulate nature of matter. During the years 1600 to 1900, many developments were made in the field of chemistry, in the study of the composition and classification of matter, and the changes that matter undergoes. The understanding of these developments is essential for the study of chemistry. A matter has a mass, and it also occupies space. A substance is a form of matter, having a definite composition, and a set of characteristic properties. These properties distinguish one substance from another substance, and give an unique identity to the substance. For example, sugar and common salt, both are white, apparently identical appearances, but common salt is salty, and sugar is sweet. In addition, there are many characteristic properties which distinguish sugar from salt. Similarly, sugar and small plastic cubes are apparently identical, but when added to water, sweet sugar dissolves, and tasteless plastic floats on water. Different substances differ from each other in their constituent composition, and can be distinguished from each other by their appearance, taste, smell, interaction with other substances, and some more simple tests, like behavior on heating, dissolution in water, reaction with acids and other reagents. Some examples of common substances are oxygen, nitrogen, carbon dioxide, water, mercury, iron, gold, sugar, alcohol, common salt, etc. A mixture is a simple combination of two or more substances in which the constituent substances retain their separate identities. The composition of mixture can be varied to any extent. Therefore, mixtures do not have fixed composition. Mixture of ethyl alcohol and water, salt and water, or mixture of gases, air constitute a homogeneous mixture. For a given homogeneous mixture, the concentrations of the constituents remain uniform throughout the mixture, and all the constituents are present in one phase. If two or more phases are present in a mixture, then it is called a heterogeneous mixture. For example, phenol water systems, silver chloride water system, iron filling sand system, etc. Mixtures of all gases constitute homogeneous system, while mixtures of all solids constitute heterogeneous system. Mixture of liquids may be homogeneous or heterogeneous. Any mixture can be formed from the components, and also can be separated into pure components by simple physical methods like distillation, filtration, condensation, etc. All pure substances are distinctly different from the mixtures, and always have fixed composition. For example, gold, silver, copper, mercury, bromine, oxygen, etc., contain only one component. Water contains hydrogen and oxygen. Methane contains carbon and hydrogen, and ammonia contains nitrogen and hydrogen. The constituents of pure substances cannot be separated by simple physical methods. Chemical reaction is a process in which substance or substances interact, producing new substance or substances. During early days of evolution, the first chemical reaction that was noticed was combustion. This was after the accidental discovery of fire. The phlogiston theory. The discoveries of hydrogen, oxygen, and formation of water from hydrogen and oxygen were the beginning of the subject modern chemistry. It is interesting to take note of the developments. In 17th and 18th centuries, the combustion reactions were explained on the basis of phlogiston theory. The theory stated that a substance undergoing combustion mainly contains a mysterious matter called phlogiston and some clacks. If a substance is burnt, phlogiston evolves and goes into the atmosphere, and clacks is left behind as an ash. When candle burns in closed container, the air in container becomes saturated with phlogiston. Air cannot accommodate additional phlogiston, and the candle is extinguished. In 1771, British scientist Joseph Priestley heated a substance, now known as mercury oxide, by focusing sun rays on it. A gas was evolved. It was observed that substances burnt in this gas more vigorously than in air. Burning candle becomes brighter in the gas. Priestley believed that the gas is the normal air without phlogiston. Hence, he named the gas dephlogisticated air. In 1766, Sir Henry Cavendish prepared another gas by reaction of dilute acid with metals like zinc, iron, etc. He named the gas as flammable air. The gas was found to burn in air, and also in dephlogisticated air, producing water, in continuation with the idea of phlogiston. Cavendish suggested that flammable air must be water associated with phlogiston. Finally, French scientist Antoine Lavoisier ruled out the theory of phlogiston. He proved that, during burning, part of the air is used in chemical reaction. The part of the air used for burning was named oxygen, meaning acid forming. He further proved that gas formed in Joseph Priestley's experiment was oxygen. He also proved that flammable air produced by Cavendish was a new gas. He named it hydrogen, meaning water forming. Elements and compounds. All pure substances are classified as either elements or compounds. An element is defined as a substance that cannot be decomposed by a simple chemical process, into two or more different substances. Some of the examples of elements known for a long time are gold, silver, copper, carbon, sulfur, and phosphorus. Till recent times, 118 elements are identified. Most of the elements exist naturally, and a few of the elements are man-made. Compounds are defined as substances of definite compositions, which can be decomposed into two or more substances by a simple chemical process. Water, sodium chloride, sugar, alcohol, carbon dioxide, acetic acid, are some common compounds. The properties of all the substances and the elements obtained on decomposition of the compounds are completely different. For example, decomposition of a compound water gives hydrogen and oxygen gases. Hydrogen gas is combustible. Oxygen helps combustion. But water is used as fire extinguisher. Chemists represent elements by symbols of one or two letters. The first letter of the symbol is always capital, and the second letter is always small. The symbols of most of the elements are derived from the English names of the elements. In some cases, Latin names of the elements are used. Above table gives names and symbols of some common elements. There are about 100 stable, naturally occurring elements. But compounds formed by these elements are more than 4 million. And the number is ever increasing. Units. Chemistry is an experimental science. Experiments in chemistry involve observation and collection of data, both qualitative and quantitative. The quantitative data deals with measurements of one or more physical properties, like mass, length, volume, temperature, pressure, time, etc. The measurement of any physical quantity involves comparison of its magnitude, or size, with a standard of the same kind. The standards are chosen arbitrarily, with some universally accepted criteria. The arbitrarily decided and universally accepted standards are called units. Any measured property is expressed as a number along with an appropriate unit associated with the property. Only number does not give any idea of the property. There are several systems in which units are expressed like CGS, centimeter for length, gram for mass, and second for time, FPS, foot, pound, second, and mks, meter, kilogram, second, systems, etc. While making calculations, it is advisable to confine to one single system of unit. NASA's Mars Climate Orbiter, the first weather satellite for Mars, was destroyed by heat. The failure of the mission was due to confusion in estimating the distance between Earth and Mars in mile and kilometers units. In 1960, the General Conference of Weights and Measures proposed revised metric system called International System of Units. That is SI system, abbreviated from its French name System International d Units. 7 fundamental SI units are listed in the above table. Number. Fundamental quantity. SI unit. Symbol. 1. Length. SI unit, meter. Symbol, m. 2. Mass. SI unit, kilogram. Symbol, kg. 3. Time. SI unit, second. Symbol, s. 4. Temperature. SI unit, Kelvin. Symbol, K. 5. Amount of substance. SI unit, mole. Symbol, moles. 6. Electric current. SI unit, ampere. Symbol, A. 7. Luminous intensity. SI unit, candela. Symbol, CD. Derived units. The units of all physical quantities can be derived from the 7 basic units. These units are known as derived units. Table. Derived units. Number. Physical quantity. Relationship with fundamental unit. Symbol. 1. Area. Length squared. Symbol is m square. 2. Volume. Length cube. Symbol is m cube. 3. Density. Mass per unit volume. Symbol is kg per meter cube. 4. Velocity. Distance traveled in unit time. Symbol is meter per seconds. 5. Acceleration. Velocity change per unit time. Symbol is meter per second square. 6. Force. Mass into acceleration. Symbol is kg meter per second square. Newton, N. 7. Pressure. Force per unit area. Symbol is kg per meter per second square. 8. Electric charge. Electric potential. Or potential difference. Current into time, or energy per unit charge. Symbol is A/S, Coulomb, C. kg, meter square per second square per ampere. Or joule per ampere. Per seconds, volt, V. Or joule per coulomb. 9. Energy. Work or heat. Force into distance traveled. Symbol is kg, meter square per second square. Or joule per seconds. 10. Concentration. Mole per cubic meter. Symbol is moles per meter cube. 11. Electrochemical equivalent. Z is equal to E upon F. Symbol is kg upon coulomb. or kg per coulomb. 12. Heat capacity. Cp is equal to dH upon dt. Cv is equal to dE upon dt. Symbol is joule per Kelvin per moles. Some common SI prefixes used for expressing big and small numbers are given in above table. Table, common SI, prefixes. Prefix. Symbol. Magnitude. Meaning. Multiply by. Tera. Symbol is T. Magnitude is 10 raised to 12. Meaning is 12 zeros on 1. Giga. Symbol is G. Magnitude is 10 raised to 9. Meaning is 9 zeros on 1. Mega. Symbol is M. Magnitude is 10 raised to 6. Meaning is 6 zeros on 1. Myria. Symbol is My. Magnitude is 10 raised to 4. Meaning is 4 zeros on 1. This is now obsolete. Kilo. Symbol is K. Magnitude is 10 raised to 3. Meaning is 3 zeros on 1. Hecto. Symbol is H. Magnitude is 10 raised to 2. Meaning is 2 zeros on 1. Deca. Symbol is Da. Magnitude is 10. Meaning is 10. Deci. Symbol is D. Magnitude is 10 raised to -1. Meaning is 0.1. Centi. Symbol is C. Magnitude is 10 raised to -2. Meaning is 0.01. Milli. Symbol is M. Magnitude is 10 raised to -3. Meaning is 0.001. Micro. Symbol is mu. Magnitude is 10 raised to -6. Meaning is 0.000001. Nano. Symbol is N. Magnitude is 10 raised to -9. Meaning is 0.00000001. Pico. Symbol is P. Magnitude is 10 raised to -12. Meaning is 0.000000000001. Femto. Symbol is F. Magnitude is 10 raised to -15. Meaning is 0.0000000000000001.